All students are requested to drop down their names for the attendance purpose. We will be starting in a short while. All students are requested to drop down their names first. Okay, so some of you have given the test. I guess Amoka and Laurel has given the pending test. And what about others? What about others? You people are requested to just give your pending test on the Conceptry digital portal as soon as possible, so that you can test your concepts according to it. So, okay, we will start with the P block elements, right? So, today we are starting with the inorganic part, basically, inorganic chemistry. So, in inorganic chemistry, you have P block, D block and coordination compounds. So, today we will starting with the P block elements, right? So, what are basically P block elements? If you see in 11th class, you must have learnt about 13th and 14th group, right? So, P block elements are the groups that are 13th to 18th basically, right? So, 13th and 14th has been completed in the 11th class itself, and today we will start with the 15th group, right? So, all about 15th to 18th group members. So, here if you see that on the left hand side table there is a S block, right? That means the last electron here is entering into the S orbital, therefore these are known as S block elements, right? So, these are the alkaline metals, then these are the alkaline earth metals, right? Here if you see that from 13 to 18 group, it is known as the P block elements. Why it is known as the P block elements? Because the last electron in them is entering in the P orbital, right? While in between the S and the P block, if you see, there are D block elements, right? So, as they are behaving as a transition between S and P block elements, therefore, the D block elements are also known as the transition elements, right? So, here the right hand side of the periodic table, you will be having group number 13 to 18, which are known as P block elements. So, if you see here that what are the number of electrons present in the outermost shell, right? If you write down the configuration here, let us say for 13 it is what? Ns2 Np1, then it is Ns2 Np2. Then it is Ns2 Np3, then Np4, then Np5, and the last one is Np6. That means what? That in the outer shell, the 13th group will be having 3 electrons. In 14th group, there will be 4 electrons, 15th group 5 electrons, 16th group 6 electrons, and 17th group 7 electrons, and 18th group 8 electrons, right? So, the electrons that are present in the outermost shell are basically 3, 4, 5, 6, 7, 8 of the respective group, that is 13, 14, 15, 16, 17, 18 groups. Okay. Now, so the last electron of these groups elements occupies the position in the P subshell. That is why they are known as what? P block elements, right? So, we have done with the general configuration. For 13 it was what? Ns2 Np1. Then for 14 it was what? Ns2 Np2. Then for 15 it was what? Ns2 Np3. Then 16 it was what? Ns2 Np4. Then 17 it was what? Ns2 Np5. Then 18 it was what? Ns2 Np6. So this means what? That the basic general configuration of the p block elements is what? Ns2 is common to all of them, so Ns2, while the number of electrons in the p orbital are changing, so we will keep it as Np126, right? So this is the general electronic configuration for the p block elements. Now what we have to study in the p block elements, basically we have to study about the physical properties, trends in the family, preparation and chemical properties of the elements, while we have to study the compounds of those elements. For example, hydrides, halides, interhalogen compounds, oxoacids, oxides, right? And for those compounds we have to see the methods of preparation, physical and chemical properties and the reactions itself, right? So basically, see, this P block is a very vast chapter. If you find out some standard books of foreign authors, let us say Hui or J.D. this is a very vast chapter. So I recommend you to kindly stick on to NCRT. Right, NCRT is more than sufficient for solving questions which are coming in competitive exams as well as the CBSE too. So NCRT is sufficient because P block is very vast and we cannot remember each and everything about each element. So therefore, I recommend that you pay attention to NCRT, right? The book recommended for this particular chapter is NCRT only. Now, see, for P block, 13th and 14th group have been done in the 11th, right? So this is known as what? The boron family, right? And this was known as the carbon family. So we are studying here the 15th group, that is the nitrogen family. So what are the elements included in the 15th group? Basically nitrogen, phosphorus, arsenic and antimony, bismuth and moscovium, right? So these are also known as nicogens and the compound as known as nicomides. Their compounds are known as nicomides. So this is the general name for group 15 elements that are known as nicogens. Here if you see, for 16th group, if you see, that is the oxygen family. The members of the oxygen family are oxygen, sulfur, selenium, tellurium, polonium that belong to the group 16 and also livermorium, right? So this is the basic unofficial name given to that compound. However, we follow the IUPAC naming, right? So these elements are known as chalcogens. H is silent, they are known as chalcogens, that is ore forming elements. Because if you see, let us say for example aluminium, right, the ore is what? Bauxite. If you see iron, right, so basically these the elements of the periodic table such as aluminium, iron, magnesium are not present in the pure form in the nature, right? They are present in the form of a ore, and ore are basically what? The compounds of oxygen and sulfur. Therefore they are known as ore forming elements. For example, if you consider Al2O3 or Fe2O3, right? So the ores are basically what? The oxide and the sulfides of the elements, and from that particular thing you can extract the metal itself. Therefore they are known as ore forming elements because they are used to form ores of particular elements. Okay. So here if you see group 17, if you see, it is known as the halogen family. It is known as the halogen family, right? So the members of this particular group are what? Basically fluorine, chlorine, bromine, iodine, astatine and tennessine, right? So these are known as what? Halogens, and they are sea salt forming elements, right? As the name suggests here, see, they form salt with the alkali metals as well as alkaline earth metals. For example, NaCl, NaBr, right, Nai, Ki. So these form salts with alkali as well as the alkaline earth metals. Therefore they are known as the sea salt forming elements. Next, the group 18. So group 18 consists of the noble gas family. It is known as what? The noble gas family, which is inert in nature. It is stable in its form, right? So the elements of this particular group is helium, neon, argon, krypton, xenon, radon and organocin, right? So amongst these, helium is the second most abundant element in the universe, right? Comment down which is the first most abundant element in the universe. Helium is the second most abundant element in the universe. Find out what is the first most abundant element in the universe. And argon is the most abundant of all the inert gases in the atmosphere. Means that if these are the inert gases, then argon is present in the maximum amount, right, amongst these. So these are known as the noble gas family or the inert gas family. Now we will talk about the general properties which you must have done in your periodic classification of elements also, right, in 11th class. So we'll just have a brush up of that. So if you see that size of the atoms increases down the group. Why does it increases down the group? Because if you see here that nucleus, let us consider nucleus. So down the group what happens is that shell number increases. Shell number increases. Like an onion, if you see over the onion bulb there are layers, right? So if you go on increasing the layers over the onion bulb, what happens is that its size increases. Similarly here also what happens that shell are added as we go down the group, and therefore it leads to the increase in the size of atoms when we go down the group. While in case of the across the period, if you see, the size decreases from left to right in a period. Why does it decreases? Because the effective nuclear charge increases. The effective nuclear charge increases from left to right in a period. Therefore, the outermost electron, if you see, is more attracted towards the nucleus itself, right? So if it is more attracted, what happens? The nucleus will offer more electrostatic force of attraction towards the outer electron, and therefore it will get contracted. So the atom gets contracted due to the more Z effective, that is effective nuclear charge. Therefore across the period left to right the size decreases. Now next, ionization energy. If you see ionization energy, first ionization energy will decrease down the group and increase from left to right in a period, right? So basically ionization energy you can relate it to size. How you can relate it to size? For example, what is ionization energy? Basically that from a gaseous isolated atom, the energy that is required to remove the outer electron is known as what? The ionization energy, right? So if there is a greater size of the atom, that means that the electron, the outer electron which is present, is offered a less nuclear charge by the nucleus, and therefore it is easier to remove the outer electron as the size increases, right? So we know that down the group size increases. As the size increases, the charge that is offered by the nucleus to the outer electron decreases, and therefore we are able to remove that electron easily, or we only require to spend a small amount of energy to remove that particular outer electron. Therefore ionization energy decreases down the group. Ionization energy decreases down the group. While in case of a period, if you see, that is left to right, if you are seeing, what happens that Z effective is increasing. That means the nuclear force of the nucleus that is acting towards the outer electron is very much, right? So it holds the electron tightly, and therefore we need to supply more energy to remove that outer electron from the atom itself. So ionization energy increases down the group. Ionization energy, increases across the period. Increases across the period. But there is an anomaly here. If you see group 15, right? Group 15 have high ionization energy than 16 group. Why? If you write down the general electronic configuration of group 15, it is what? Ns2 Np3, right? While in case of group 16, if you write down, it is Ns2 Np4. So here if you see that it is P3, that means the shell is half filled, right? So here if you say there will be more electron repulsion, more electron repulsion, but here if you see it is half filled, therefore it is less electron repulsion, and therefore this particular half filled configuration is stable, right? So as this particular thing is stable, so if you want to remove that electron from a stable atom, basically it will have a high ionization energy. But if you want to remove from Np4, it will readily lose an electron to become Np3, so that it gets half filled configuration, which is more stable as compared to that of the Np4, as electron repulsion decreases in the case of half filled configuration. Okay. Next, moving on to the electron affinity. So electron affinity, if you see, increases from right to left along the period. Electron affinity increases from left to right in a period. What is electron affinity? Basically, the tendency to gain an electron in the form of a isolated gaseous atom is known as what? The electron affinity. See, there is a difference between the electron affinity and the electronegativity, right? Electron affinity, if you say, it is the tendency of gaining electron in a isolated gaseous atom, but electronegativity, if you see, that atom is in the bonded state and the tendency of the atom to attract the shared pair of electrons in a compound is known as what? Electronegativity. So, if you are talking about, let us say, hydrogen is gaining an electron, hydrogen atom, isolated gaseous hydrogen atom is gaining an electron, then it will be termed as what? Electron affinity, right? But if you are saying, let us say that a hydrogen and oxygen bond, then you will talk about what? Electronegativity, that oxygen is having a greater electronegativity. This means that the tendency to attract the shared pair of electrons between oxygen and hydrogen is more towards the oxygen. I hope I am clear. So, if you say electron affinity, it increases from left to right while it decreases from top to bottom. That means, if you see from left to right, that is, when you go from S block to P block, the elements tend to gain electrons. The element tends to gain electron, while if you see down the group, that is moving down the group, the electron affinity decreases, right? That means the tendency to gain electron decreases, right? But here if you see, again an anomaly comes, that group 15 is having exceptionally low values of electron affinity. Why? Because group 15 is having a electronic configuration of ns2np3, so it is already stable. If it will gain electron, it will become what? np4, and it will become unstable because there will be electron repulsion now, right? So therefore the group 15, due to its half filled p subshell and stability that is caused due to that half filled p subshell, it is having exceptionally low values of electron affinity. Similarly, if you see group 18, that is having a configuration of ns2np6, right? It requires no electron, it is stable in itself, so they are having zero affinities. They are having what? Zero affinities, because they are having a complete octet which provides them stability. Now coming on to the metallic character, if you see, the metallic character is governed by the size of atoms and ionization energy, right? So here if you see that down the group, what happens here is that size of atom increases. Size of atom increases, right? And down the group also ionization energy decreases. Ionization energy decreases because there is an increase in the size, so there will be lesser force of nucleus towards the electron. So what will happen, that the elements which are having bigger size and low ionization energy has a greater metallic character. So among this group, let us say in the boron family, this particular element if you see will be the largest atom in the size, and its ionization energy will also be the least among the all elements that are present in the group. So therefore it is the most metallic in nature in a particular group. That means what? That the metallic character if you see increases down the group. Metallic character increases down the group, while vice versa you can say that across the period metallic character decreases. Metallic character decreases. So basically a period starts with what? Alkali metals and alkali earth metals, right? Alkali metals and alkali earth metals, and it ends up with what? Halogens and oxygen family, nitrogen family. So here if you see that across the period what is happening, the non-metallic character is increasing, therefore nitrogen, oxygen, fluorine are what? Basically non-metals. But if you compare here sodium, magnesium, they are metals. So this shows that metallic character decreases across the period while increases down the group. Okay, so here if you see in the nitrogen family, oxygen family, fluorine family, what is happening, that the lower members here are the metals, right? For example, let us take bismuth. Bismuth is a metal, and the metals and the non-metals are separated by this particular yellow line, and some elements that lie on this particular line are known as what? The metalloids. Are known as what? The metalloids. What are metalloids? Basically the elements which are having the property between of metals and non-metals are known as what? Metalloids. Okay. Now, yeah, I forgot to mention silicon, germanium, right, antimony. These are what? Basically the metalloids. Okay, and above it are the non-metals, boron, carbon, nitrogen, oxygen, fluorine, and below it are the metals, that is lead, bismuth, right. These are what? Basically the metals. Now, here if you see oxidation state, so the p block elements, if you see, they have variety of oxidation state, but in case of s block, if you see s block, alkali metals were having +1 oxidation state and alkaline earth metals were having +2 oxidation state. So the oxidation state here was fixed, but for d and p block, if you see, both are having variable oxidation states. Both are having variable oxidation state, that is tendency to show more than one oxidation state is known as what? Variable oxidation states, right. So some of the oxidation states are positive and some of the oxidation states are negative, but if we see a trend here, what is happening, let us say that boron family, if you take, the common oxidation state is +3 basically, right. But when you move down the group, the stability of the lower oxidation state, stability of the 2-unit lower oxidation state. So what is 3 minus 2? That is +1, is increasing as we go down the group, right. Similarly for carbon here also, for carbon family, +4 is, let us say, that is the common oxidation state. So when it comes to tin and lead, what is happening, that +2, that is the 2 units less than that of the common oxidation state, is becoming more and more stable as we move down the group, right. Similarly here also, if you see that +5 is the common oxidation state for all the elements of group 15. So as you move down the group, what happens, that basically the antimony and bismuth are more stable in 2 units less, that is the +3 oxidation state, and this extra stability of the lower oxidation state as we move down the group is known as what? The inert pair effect. Inert pair effect. So why this inert pair effect is shown by the elements which are present at the lower bottom of the group, or the heavier elements of the particular group, because d and f orbitals starts filling out, right, and d and f orbitals are poor at shielding, so they cannot shield the s electrons that are present in the outermost orbital, and therefore attraction between the outer s orbital and nucleus is more. So those s electrons are not ready to come out of the atom itself, right. So s is having how many electrons? 2 electrons, right. So these 2 electrons, when we move down the group, they are not ready to come out of the atom itself. So what happens, that only 2 oxidation state, that is 2 unit oxidation state, is less than that of the common oxidation state in case of heavier members. Is it clear? Is it clear? Give a thumbs up in the chat section box and let me know. Concept of inert pair effect. Okay. Yeah, Sham, we will discuss the oxidation states one by one, right. First we will discuss the group 15, then 16, then 17. So we can do in detail group wise, okay. This is a general thing. So in detail, that is the oxidation states, the variable oxidation state that are shown by group 16 can be discussed when we will discuss group 16, okay. Okay, so next we will move to the general properties. So we have seen that along the period left to right, atomic radii decreases, ionization energy increases, electron affinity increases, electronegativity increases, metallic character decreases, oxidizing property. Now this is important, that is oxidizing property means what? That the tendency to oxidize others or reduce themselves, right? Reduce means what? That they will gain electron, and we are already knowing that electron affinity is increasing across the period, is increasing across the period. That means the tendency to gain electron is increasing across the period. That means the elements which are present at the right hand side of the period will tend to reduce and oxidize other, right? So therefore the oxidizing property, that is the tendency to oxidize other and reduce yourself, increases here. And also for the reducing property, if you see what will happen, that reducing property will decrease, right? Because the electron affinity, if you see, it is increasing across the period. So the tendency to act as a reducing agent lowers. Why? Because they will not lose electron, as ionization potential also increases across the period, so they will not lose electron. Therefore reducing property decreases along the period. Okay. Yeah, so this is the question: why the first ionization energy of group 15 elements much higher than those of corresponding group 14 elements? Why? Why group 15 elements are having higher ionization energy than that of the group 14 elements? Anyone? Anyone? Refer to the electronic configuration. General electronic configuration of group 15 elements is what? Ns2 Np3, right? That means, yeah, Arun, you are correct, due to extra filled d orbitals. Half filled stable configuration, yeah, good. Nilambri, you are correct. Arun, you are half filled p orbitals, not d orbitals but p orbitals. Okay, so here if you see that group 15 element is having Ns2 Np3, so this is exceptionally stable, right? So if you want to remove electron from a stable configuration, it will take a lot of amount of energy. But if you see group 14, it will have a general electronic configuration of Np2, so it is not that much stable as that compared to the half filled configuration, and therefore it can easily lose electrons, so the ionization energy is less here. Okay. Now, second question comes: second ionization energies of the carbon, nitrogen, oxygen and fluorine atoms are such that A, B, C, D. What should be the answer? Second ionization energy you have to calculate, not the first. Second ionization energy. Energy that is required to knock out the second electron. You can write down the electronic configuration. What is the electronic configuration of carbon, nitrogen, oxygen and fluorine? This is Ns2, Np5, Ns2, Np4, Ns2, Np3, Ns2, Np2, right? Now, you are asked about the second ionization energy. So, first we will remove the first electron, that is Ns2, this will remain, this will be Ns2, Np2, this will be Ns2, Np3 and Ns2, Np4. Now from this particular configurations, that is this one, you have to remove a electron. You have to remove a electron. This one is carbon. You have to remove a electron. So you can see here what is happening, that Ns2 Np3, if you see, it is the half filled stable configuration. Half filled stable configuration, right? And also we know that ionization energy increases across the period. Ionization energy increases across the period. So what should be the trend here? What should be the trend? A, B, C, D. Okay, so D, okay. Arun is saying D, Sham is saying D, Tasneem D. Let us see what's the answer is. Yeah, your answer is correct. It is D, right? So oxygen, if you see, because it is half filled, it will be more stable, and therefore it will be, it will require greater energy to remove out the second electron, right? That is the electron from NS2 NP3. Now, if you compare the electronegativities of fluorine, nitrogen and carbon, or the ionization energy of fluorine, nitrogen and carbon, because fluorine is very electronegative in nature, it will not give out its electron easily, right? So therefore the second one is fluorine, then nitrogen, and then carbon. This anomaly here is there because of the half filled stable configuration, right? Otherwise the expected order should be this, right? But here it is swiping out because oxygen is extra stable due to its half filled configuration. Yeah, you all are correct with your answers. Very good. Next, move on. The element with atomic number 117 has not been discovered yet. In which family would you place this element if discovered? Element with atomic number 117. For these type of questions, just remember the atomic numbers of noble gases, right? And then you can back calculate probably. How will you do this question? See here. You will remember 2, 10, 18, 36, 54, 86 and 118. So 117 would be close to 118. So it is 1 electron less than that of 118. That means 117 will be a group prior to that of the group 18, and so that it is present in the halogen family. It is present in the halogen family. Similarly, if I ask about that, for example, tell me that where should I place atomic number 84? So, you know that 86 is the atomic number for radon, and if you minus 2, that means you are moving 2 groups before that of the noble gases, that is group 16. So, you will place 84 in group 16. So, you can particularly learn the atomic numbers of noble gases, and then you can back calculate. Right, helium, neon, argon, krypton, xenon, radon, and then 2, 10, 18, 36, 54, 86, 118. Okay, yeah, you all are correct that the answer is C. Very good. Next, we will be doing with the 15th group. Right, first we will start with the 15th group. Now we will discuss in details about all the groups. Here if you see, the group 15 of the periodic table consists of what? Nitrogen, phosphorus, arsenic, antimony and bismuth, right? So these elements are known as what? Nicogens, and their compounds are known as what? Nicomides. So as we go down the group, what is happening here? Down the group, size will increase, ionization energy will decrease, metallic character will increase. So this means that if you take bismuth, it is a metal. If you take arsenic and antimony, these are what? Metalloids. And nitrogen and phosphorus, these are what? Non-metals. So this proves that what? That metallic character increases down the group. Or you can vice versa say that non-metallic character decreases down the group. So nitrogen gets its name from a mineral which is known as nitre, right? That is potassium nitrate. So if you see the occurrence and general properties of these particular elements, so we are very much confirmed that nitrogen is present as nitrogen gas in the atmosphere, and it occupies 78% volume of the atmosphere, right? And in the earth crust, if you see that nitrogen is present as sodium nitrate, that is the child saltpeter, and potassium nitrate, that is the Indian saltpeter, right? So, and also it is found in the form of proteins in plants and animals, right? So this is the basic occurrence of what? Nitrogen. Phosphorus, if you see, phosphorus is formed from the Greek word that is phos and phoros, that means light bearer. So phosphorus occurs in minerals of the apatite family, which are basically the phosphate rocks, right? So this important thing you can remember, that phosphorus is present in phosphate rocks, right? And such as fluoroapatite, right? Or for example, calcium fluoride with a salt of calcium 9 phosphate 6. That means these are the composition of basically what the phosphate rocks, right? So phosphorus is an essential constituent of animal and plant matter also. It is present in the bones of the living cells, and also phosphoproteins are present in the milk and eggs also. Okay, so phosphorus is present in phosphate rocks, is it present in milk, it is present in eggs, it is present in animal and plant matters, and also in bones as well. So phosphorus has three allotropes, that is the white phosphorus, red phosphorus and black phosphorus. So the structure of phosphorus allotropes is very important. Structure is very important, and stability, that amongst which one is thermally stable, is also a frequently asked question in the examination, right? So there are three allotropic forms, that is white, red, black. White is also known as yellow, that we will discuss in the next slide, that why it is also known as the yellow phosphorus also. So if you see white phosphorus, it is a translucent white waxy solid. It is poisonous in nature, right? And it is insoluble in water but soluble in carbon disulfide. That means it is insoluble in polar solvent but it is soluble in non-polar solvent. It glows in dark, that means it is chemiluminescent, right? So white phosphorus is less stable. This you have to remember, that white phosphorus is less stable and therefore more reactive, right, than the other phosphorus allotropes, that is the black and the red phosphorus. So if you see that what is the property of white phosphorus that is making it reactive, basically is the angle strain. So if you consider the structure of white phosphorus, basically it is what P4 structure, right? So a rhombohedral on which each corner you are placing the phosphorus atoms, and they are also interconnected diagonally. So if you see, there is an angle strain of 60 degree here, right, while the tetrahedral geometry has an angle of 109.4 degree approximately, right? So here if you see that due to the much angle strain, what is happening, that this is become the white phosphorus is becoming very much less stable and more reactive. So white phosphorus, what happens, that is dissolves in NaOH and yields to phosphine gas, that is PH3, and sodium hypophosphite, that is NaH2PO2. And this one is very important, that white phosphorus readily catches fire in air, right, and it gives dense fume of P4O10. So P4O10 will be a oxide of phosphorus only, and its structure is very important from the examination point of view, and in the further sessions we will be discussing its structure too. So P4O2 on reacting with oxygen will give you what? P4O10, that is particularly the oxide of the phosphorus. Now next, containing the red phosphorus, if you see, so red phosphorus is obtained by heating white phosphorus at 573 Kelvin. That means if you heat white phosphorus at 573 Kelvin, you will obtain what? Red phosphorus, right? So red phosphorus possesses iron grey luster. It is odorless, it is not poisonous, it is insoluble in water as well as carbon disulfide. So you can see here that what is the difference in structure of the red phosphorus and the white phosphorus. Basically, if you see that there is no one diagonal missing here, one diagonal connection is missing in the red phosphorus. So red phosphorus basically occurs in the polymeric form, right? So chemically, if you see that red phosphorus is very much less reactive as compared to that of the white phosphorus, and also it is not chemiluminescent, that means it does not glow in dark. So allotropes are also very important from the examination point of view, especially for the phosphorus and for the carbon, right? So why white phosphorus is also known as yellow phosphorus basically. So if you take freshly prepared phosphorus, right, so freshly prepared phosphorus is basically colorless. On standing, what happens is that it acquires a pale lemon color. Why does it acquire a pale lemon color? Due to the formation of red phosphorus on the surface, and therefore it is also known as what? Yellow phosphorus. Okay. Black phosphorus, if you see, black phosphorus has two forms, that is alpha black phosphorus and beta black phosphorus. So alpha black phosphorus is formed when red phosphorus is heated up to 803 Kelvin. right? Alpha phosphorus is formed when red phosphorus is heated up to 803 Kelvin. So if we heated white phosphorus, is what it was converting into red phosphorus. Then if we heat red phosphorus, it is converting into black phosphorus, right? And it can be sublimed in air and has opaque monoclinic and rhombohedral structure. This is very important, that black phosphorus is having monoclinic and rhombohedral crystals, and also it does not oxidize in air. That means it is very much stable. It is not reactive as that of the white phosphorus. Coming on to beta black phosphorus, is prepared by heating white phosphorus at 473 Kelvin under high pressure, and this particular thing is very important, that it does not burn in air up to 673 Kelvin. That means that it is thermally stable. It is thermally stable. Okay. Now this one is also very important. It is used in matches, explosives, rat poison, and it fertilizes, and also in alloys phosphorus. And matchbox, if you see, its sides contains, that is the red part, right, which you strike basically, it contains of the red phosphorus or P2S3 and sand and glue. While on the tip of the matchstick, if you see, it consists of red phosphorus, oxidizing agents like KClO3 or potassium nitrate or lead oxide basically, and a glass powder or chalk for friction plus glue. So what happens, that when you rub the tip of the matchstick on the side of the matchbox, a friction is created, and due to that friction, that particular matchstick catches fire. Okay. So why white phosphorus is stored under water? This we have already done, that white phosphorus is very much reactive, right? So to prevent it reacting from atmospheric oxygen, we keep it under water, right? And also the similar question was that why sodium and potassium metals are kept in the kerosene oil. Why? Because they react vigorously with the atmosphere or the air basically. So therefore they are kept in kerosene oil. Similarly here also, if you see that white phosphorus is stored under water so that it cannot react with atmospheric oxygen. Which of the following allotropic form of phosphorus is thermodynamically more stable? So we have already done that, what, black phosphorus, if you see, that it is the thermodynamically more stable because it does not decompose up to a greater temperature upon heating. Which allotropic form of phosphorus is used in making matchsticks? So red phosphorus, if you see, is the allotropic form of phosphorus amongst the white phosphorus, red phosphorus and black phosphorus. Red phosphorus is used in making of the matchsticks. So arsenic, antimony and bismuth, they are mainly found as sulfide minerals, right? So arsenic is a trace element. What do you mean by trace element? That it is not required in a much amount by our body, rather a small amount of it is enough for humans, red algae, chicken, rats, goats and pigs, right? So a deficiency of arsenic results in inhibited growth. That means the particular living being that is having a deficiency of arsenic will not grow properly, right? So most infamous use of arsenic is a poison, that it is acting as a poison also. And arsenic is also used in semiconductor devices. So what are semiconductor devices? We have already done in electrochemistry also, that there are conductors, semiconductors and insulators. So semiconductor are those devices which are having a conductivity as that of between of the conductors and the insulators, right? So the name antimony is derived from the Latin word that is anti plus monos, that means not alone, right? So the symbol for antimony comes from its original name, that is tibium, right? So the standard state of antimony is solid at 298 Kelvin. That means antimony is present as a solid and it is very brittle, right, and flakes easily. What do you mean by that, flakes easily? That it converts into smaller particles easily, right? It breaks easily. Antimony has a bluish white metallic sheen, right? It is a poor conductor of heat and electricity. It is known to be severely toxic. It causes damages to the liver and used in some cases to induce vomiting and sweating. So the next time you want to skip your schools or colleges, you can take antimony. I am just kidding, right? So basically it is used to induce vomiting and sweating, right? So it is added to iron and iron alloys to increase its hardness, right? So iron, if you see that to particularly increase the hardness of the iron, we can add antimony also, and adding antimony will also reduce corrosion of iron. So antimony sulfides are used in vulcanization of rubber also. That means basically the preparation of rubbers. Just a second. Yeah, so preparation of rubbers as well as in pigments also. So bismuth, if you see, is the heaviest non-radioactive naturally occurring element. So it is a non-radioactive element, also it is occurring naturally. It is a hard brittle metal with an unusually low melting point. So bismuth is a metal basically, right? So you must not consider that all the elements of P block are non-metals, right? There are some elements which are metals also, and then some elements which are metalloids also, and there are some elements which are non-metals. So bismuth is basically a white silvery crystalline brittle metal with a pinkish tinge, right? So it is basically whitish or silvery pinkish. So it is rare metal because it is associated with copper, lead, tin, silver and gold ores. That means the ores of gold, ores of silver, ores of tin, ores of lead, ores of copper are also containing some amount of bismuth. So its unusual property is to expand upon solidification, right? So when you solidify it, basically what happens is that it expands, right? So therefore it is used as alloy and for coating because of its expanding property. So bismuth is used in cosmetics and also to the coloration of the glass. So you have seen that some people have glasses which are having pink colored glass or yellow colored glass or multicolored glass. So there we can use bismuth. Now coming on to the electronic configuration, if you see, so atomic number, if you see, that increases down the group, already we know. Atomic mass also increases down the group. Electronic configuration, if you see, it will be what? 2s2 2p3 for nitrogen, 1 shell added, 3s2 3p3 for phosphorus, 1 shell added, 4s2 4p3 for arsenic, 1 shell added, 5s2 5p3 for stibium or antimony, 1 shell added, 6s2 6p3 for bismuth. So in these elements, s orbital is completely filled while p orbitals is half filled, which makes them extra stable, which makes their electronic configuration basically extra stable, and therefore it shows anomalous properties as compared to the regular trend. Now here if you see, covalent radii increases down the group, right? So from nitrogen to bismuth, if you see, there is an increase in the covalent radii. That we have already discussed, that Y size basically increases down the group. And from arsenic to bismuth, if you see, can you see here, it is only a 20 and then 7. Difference of 20 picometer, difference of 7 picometer. So the increase in the radii as we go down the group becomes small, right? There is an increase, but there is not a considerable amount of increase. Why? Because if you are having let us say this from going to arsenic to antimony and antimony to bismuth, what happens is there is d and f orbital electrons start filling up, right, which are a very poor shielder. So what happens is that the outer s electrons, if you see, they are, due to the poor shielding, they are more attracted by the nucleus itself, which causes contraction, right? So therefore if you see that the increase is less as we move down the group. Ionic radii also, if you see, that it increased down the group, but here if you see, that it is 76 and this is 222. That means this is decreasing. No, it is not decreasing. Actually what is happening here is that bismuth, if you see, it is a metal basically, right? So it is electropositive, it tends to lose electron. While nitrogen and phosphorus, if you see, these are non-metals, they tend to gain electron, right? So if they gain electron, they will become what? Anions. They will become what? Anions, right? And if they lose electron, they will become what? Cations. They will become cations. So we already know that from a parent atom, if you compare the sizes, the anions are greater than that of the parent atom. The size of the anions is greater than that of the parent atom, while the size of the cations is less than that of the parent atom. Therefore, this is a decrease in the size here that is noticed from arsenic to stibium or antimony. Hope I am clear. Am I clear till now? Okay. So next we consider the ionization enthalpy. So ionization enthalpy, what does it do? It basically decreases down the group. Why does it decreases down the group? Because the size is getting increased. If the size is getting increased, what will happening? That the outer electrons are not much greatly held by the nucleus itself, right? Because the distance is very much bigger. So what happens? That the ionization of that particular electron is very easy. So we can just put small amount of energy and basically remove the outer electron from a bigger atom, right? So ionization of nitrogen is very high because of this small atomic radius. Because of this small atomic radius, the outer electron are very much attracted towards the nucleus itself, and therefore it is very hard to ionize that particular electron or knock out that particular electron from the nitrogen atom. This we have already done, that why ionization energy decreases down the group. Ionization enthalpies of 15th group are more than that of the 16th group. Why? Because the 15th group, if you are seeing that it is of NS to NP3. So what is happening here? That it is extra stable, right? And due to this extra stability, basically it is more tougher to remove an electron from a half filled stable electronic configuration rather than that of NP4, right? NP4 will readily lose electron to form NP3, so the ionization energy should be less, but NP3 will not now lose electron because of the extra stability of the electronic configuration. Electronegativity, if you see, electronegativity decreases down the group. As the atomic size increases, electronegativity decreases down the group. What is electronegativity? Basically, electronegativity is the property by which the atom attracts the shared pair of electron towards itself. I am again repeating that there is a difference between the electron affinity and the electronegativity. Basically, electron affinity is the tendency of gaining an electron in the isolated gaseous atom stage, but in electronegativity we will be consider a chemical bond, right, between a molecule. If you say that there will be electronegativity between the bonded structure of an atom when it is forming a bond with a particular atom. So what is happening? That there will be a sharing of electrons. When there will be a sharing of electrons, electronegativity means that amongst the two different atoms, one will have a greater tendency to attract that shared pair of electron towards itself more. Okay. So electronegativity, if you see, it decreases down the group, and high electronegativity of nitrogen, if you see, it gives dipole movement to its compound. For example, if you see, let us say ammonia, right? So ammonia, if you see, nitrogen, hydrogen, hydrogen, hydrogen and lone pair, right? So basically, if you consider this NH bond, what is happening? That nitrogen is pulling electron here also, here also, here also. So the resultant dipole moment is coming out to be this. That means the compounds of nitrogen are polar basically because of their electronegativity of nitrogen. Similarly, if you consider the oxidizing and the reducing nature, basically oxidizing nature means that it is reducing itself, it is reducing itself and oxidizing other, reducing itself and oxidizing other, right. So what will happen here, that nitrogen, because it is having a greater electron affinity, it attracts electron. What will happen, that it will tend to reduce itself and oxidize other. Therefore the oxidizing power is maximum uh, of nitrogen compared to the other group members. If you consider the reducing power, basically the power to reduce other and get oxidized self. So what will happen here, that bismuth being a metal will tend to lose electron, because metals are electropositive in nature, and therefore it will readily get oxidized and reduce the other species. Therefore the reducing power, if you see, it will increase down the group, oxidizing power will decrease down the group. Okay. Next is the physical state. So if you consider, except nitrogen, all other members of the family, that is the nitrogen family, are normally solids, but nitrogen is what, basically a gas, we all know that. So melting point, if you see melting point depends upon the structure, right, structure of that particular element, while boiling point, if you see, it depends upon the molecular mass or the atomic mass basically, right. So here if you see that melting point increases from nitrogen to arsenic, this is attributed to their structures basically, right. And nitrogen exists as a diatomic molecule, we already know that, N triple bond N. So nitrogen exists as N2 in the elemental state, while phosphorus, if you see, it exists in different allotropics form, that we have already done, white, black, red. And bismuth has a lower melting point than that of the stibbium or the antimony. Why? Because in bismuth, all 5 electrons do not participate in metallic bonding. We have discussed the metallic bonding in the solid state itself, that how the metal atoms are basically bonded in the different metals, right. So in bismuth, all the 5 electrons do not participate in metallic bonding, therefore it is having a lower melting point. But if you see the boiling point, if you compare the boiling point, there is an increase in the atomic mass as we go down the group, therefore there is an increase in the boiling point also as we increase down the group, right. So density, if you see, density is what, basically mass upon volume, right. So moving down the group, mass also increases and volume also increases, but the increase in mass is more as compared to that of the volume, and therefore as mass is more increasing, therefore density increases down the group. Okay. So boiling points we have already done, that they are increasing regularly on moving down the group, except nitrogen, all other members are solids, this also we have done. Comparing the electron affinity, so small size of nitrogen makes its electron affinity very less owing to repulsions on incoming electrons. So what is happening here, basically, see, if you add electron to a particularly smaller atom, right, so what happens here is, although it is electronegative, it likes to gain electron, but the other electrons show electron-electron repulsion towards the incoming electron because of the small size. They say that there is not much space inside the atom, and therefore addition of more electron will cause an electron-electron repulsion, better you keep outside only, right. So that is why the nitrogen makes its electron affinity very less because of the small size of it, right. For example, if you consider oxygen, right, if you make it gain 1 electron, it will convert into O negative. So the electron affinity here will be what? Negative basically, right. But if you now give electron to O minus, that is to convert it into O2 minus, now the electron affinity is positive. That means we need to give energy to put an electron into the O minus. Why? Because this particular electron will suffer electron-electron repulsion, as the size of the oxygen is also very low, and also it is carrying a negative charge already, right. So in that case, we have to give energy to that particular O negative atom, so that we can make this 1 electron enter into the O negative. So this is the summary of the trends of the group. Atomic radii we have already done, increases, ionization energy decreases from group, right, we are talking about group, down the group. Electron affinity decreases, metallic character increases, oxidizing power decreases and reducing power increases. Coming on to the oxidation states, if you see that there are variable oxidation states that are shown by the 15th group. So, nitrogen is having a oxidation state of -3 to +5, phosphorus is also having -3, +3, +4, +5, arsenic, sorry, it is +3, +5, and antimony it is +3, +5, bismuth also it is +3, +5. So, if you notice nitrogen, it is having the maximum number of oxidation states within its group, right. So, here if you see that N25, N2O5, HNO3, NO3 negative, it is bearing a +5 oxidation state. Then in NO2, N2O4, it is having a +4 oxidation state. HNO2, NO2 minus NF3, it is having a +3 oxidation state. NO, it is having a +2, N2, it is having 0, then -1, -2, -3, that means from +5, -3 to +5, basically it shows all oxidation states, but the common oxidation states are -3, +3 and +5. Okay. So, the tendency to exhibit -3 oxidation state decreases down the group. Why does it decreases? Because the metallic character is increasing, right. So, if metallic character is increasing down the group, what will happen? It will tend to lose electron, it will not gain electron, right. So, -3 oxidation state means that it is gaining 3 electrons. So, bismuth, if you see, it never shows -3 oxidation state, right, because it is a metal, it will like to give electrons rather than that of accepting it, right. So, bismuth hardly forms -3 oxidation state compound. Coming on to stability of +5 oxidation state, I have already told you that due to the inert pair effect, the higher oxidation state stability decreases down the group, whereas the lower oxidation state stability increases down the group. So, bismuth 3 plus is more stable than that of the bismuth 5 plus, right, and nitrogen 5 plus is more stable than that of the +3, right. Why? Because the tendency of the higher oxidation state stability decreases down the group, while the tendency of the lower oxidation state stability increases down the group due to the inert pair effect, that is the introduction of the D and F electrons. Similarly, -3 oxidation state is exhibited by elements when they combine with metals. Now, this is very important. Obviously, if you take nitrogen, phosphorus, arsenic or antimony, basically what is happening here is if you combine it with a metal, so metal will lose electron. So, ultimately these compound will what? Gain electrons. So, therefore, they are having a minus oxidation state when they are combining with metals. For example, calcium nitride, calcium phosphide, right, these are having what? The -3 oxidation state of nitrogen and phosphorus. Similarly, here -3 oxidation state of arsenic. Similarly, here -3 state of antimony. Similarly, here -3 state of magnesium of bismuth. Why? Because magnesium is more metallic in nature than that of bismuth. So, what happens here that magnesium will have a greater tendency to lose electron and bismuth has no option rather than to accept electron. So, for nitrogen phosphorus, if you see, yeah, lanthanide contraction is the same only, right, because of the 4f orbitals. If you see 4f orbitals, when they start filling, what is happening here, that the outer s electrons, if you see, f orbital electrons are not able to provide a good shield to the outer s electrons. So, what happens here is that these s electron, outer electrons are more attracted towards the nucleus, right. When they are more attracted towards the nucleus, there is a contraction in the size that is known as lanthanide contraction. Due to this, the 4D and the 5D series are also having the same sizes. For example, zirconium and hafnium are having the same size because of the lanthanide contraction. So, for nitrogen and phosphorus, nearly all intermediate oxidation states disproportionate. So, here if you see, what is the oxidation state of HNO2? +1 plus X minus 4. So, this will give you what? X equals to +3. Here if you see, what is the oxidation state of nitrogen? +5, and here it is what? Basically +2. So, the intermediate, that is the +3 state, is being disproportionate. That means it is being oxidized and it is being reduced also. This type of reaction is known as disproportionate reactions, where a single species is being oxidized and reduced, right, simultaneously. So here if you see +3 to +5, nitrogen is getting oxidized, +3 to +2, it is getting reduced. So it is a disproportionation reaction. So nitrogen, if you see, it is having a maximum covalency of 4, right, available for bonding. So it cannot make more than 4 bonds, right. But if you see here phosphorus, it is able to combine to 6 fluorine. Why? Because it is having an empty d orbital. So the extra electrons which are given by fluorine are kept in that particular d orbital. While in nitrogen, if you see, that is the first member of every group, d block element or the d orbital is missing, right. D orbital is missing, and therefore due to the absence of the d orbital, they are not able to expand their octet. Yeah, so that's all for today. In next class, we will be doing compounds of 15th group, that is the halides, oxides, their preparation and their properties. Okay, so we'll meet you in the next session, and also I request you to kindly complete your lagging work, that is the complete the test that are there in the conceptory digital portal. Only 2 of them, I guess, Laurel and Amoka, have completed the pending assignments. Okay, so that's all for today. Thank you. Happy learning to all.